Hello and welcome back. In this video, we uncover a really nice way to compute the dot product between two vectors that doesn't involve finding any angles between them and just involves simple arithmetic. And I'm sort of giving it away at the beginning here, u dot v, so u expressed as in component form u1, u2, u3, v is v1, v2, v3, ends up being u dot v is the product of the first two components plus the product of the second two components, plus the product of the third component. Or if I'm in two dimensions, I would just have u1, u2, v1, v2. I would skip the third one, and it would still look like this, just with this term gone if I was in two dimensions and not three. So that's our really nice, I wasn't kidding. It's a super easy way to compute dot products, as long as we have these in component form like this. So the big question is why? Why does it have such a nice form? Well, that's the rest of this video, is discovering why this formula is true. So let's have at it. Let's figure this out. Why is it so nice? Well, this is going to come from really two main sort of starting points. One is the law of cosines. Now, you might not have seen this for a very long time, but what this is a generalization of the Pythagorean theorem to triangles that are not necessarily right. So given two vectors, let's say u and v, something like this, u and v. Well, there's I really just want to think about this like a triangle. I'm not going to introduce vectors yet into this. Let's just think of it like a triangle. If I have a triangle that's not necessarily right, I'm going to call one side, let's say A. We're just thinking of lengths now, not necessarily vectors. So A, and then I have another side, let's say it's not a right triangle, so something like this, B. And then I have this third side here, let's call that C. So if it were right, we would have that C squared is equal to a squared plus b squared. But if it's not a right triangle, then this angle between them, we need to involve this angle between them. We need to adjust this quantity. C is not exactly a squared plus b squared. In this case, it's going to be a little bit less. Why is it going to be a little bit less? Well, by the law of cosines, this is actually 2ab cosine theta. Right? If b were coming off perpendicular to a, c would be a lot bigger, and so we're subtracting this quantity. If b is bigger than pi over 2, c would be longer than if it were a right triangle. So this is our law of cosines. And then there's another fact that comes from the geometry of vector subtraction. So now I'm going to bring vectors in. Imagine I have two vectors. I'm going to call this one u, and let's say we have v. I want to make it similar to my picture up here. Do you remember, I mentioned this pretty briefly in an earlier video, but u minus v, we can draw u minus v by first computing minus v, and then doing our vector addition. It's gonna be coming this way a bit, like this. But another way I can get u minus v is by taking the head of v and connecting it to the head of u, like this. Right? And one way you can kind of confirm that this is true, and I'm not trying to pull something under the rug, minus v would come down like this, add it to the head of u, and I'd get a vector coming across like this, which is exactly equal to this one. So the geometry works out here. This vector here is u minus v. So here's sort of two starting points, two things that we know, and they look sort of similar. So here we're dealing with length, so that means I'm going to be talking about magnitudes down here. Let's see. So we can get a hold of the magnitude of u minus v. We would get a hold of that by using the law of cosines if we're just looking at lengths. So applying the law of cosines to this figure gives us that. Actually, let me maybe put it up. Let me put it up here. Gives us that the magnitude of u minus v, this vector, is equal to a squared, that's the magnitude of u, squared plus magnitude of v squared, that's my b in this situation, minus 2 uv cosine theta. UV cosine theta, boy oh boy, that's the dot product of u and v. So, law of cosines applied to vectors, the dot product kind of comes out as a term. So what I'm going to do is I'm going to solve for this dot product in terms of these other quantities. So that is, c squared. There should be a squared here. Maybe you caught that, maybe you didn't. If you caught it, excellent. If not, keep a closer eye on me. I might forget stuff. So I'm going to solve for u dot v here. So that means I'm going to subtract magnitude u squared, magnitude v squared, and I'm going to divide it by 2. Or rather, I'm going to move this over to the other side so that it's positive, and then I'll divide by 2. So really what we're looking at here, if you need to, take a second, do this on your own on a separate sheet of paper. U, v, magnitude u times magnitude v, cosine theta is going to be 1/2. And I moved that over to this side. I'm going to subtract this over 1/2 of u squared plus v squared minus u minus v squared. Okay, so now we have this, and this, again, remember, this is the same as the dot product. This is the magical thing that happened, is this sort of popped out. So now I have another expression for the dot product that doesn't involve the angle between the two vectors. Great. Can we simplify this? Yes, of course we can. Magnitude of u minus v. So what I need here is my vectors in component form. So I'm going to say u is, we're going to write it as u1, u2, u3. And of course, all of this can be taken down to 2 dimensions if you just drop the third component. It's not hard to go from 3 dimensions to 2 dimensions. So let's say those are my 2 vectors. Then let's see, magnitude of u, so magnitude of u then, squared, right? Magnitude of u is going to be square root of each of these components squared added together. So when I square that, it's going to get rid of the square root. So this is going to be u1 squared plus u2 squared plus u3 squared. Magnitude of v here is going to be v1 squared plus v2 squared plus v3 squared. I forgot my square again here. And then what about u minus v squared? Well, we're going to have to compute u minus v first. So that's u minus v is going to look like u1 minus v1, u2 minus v2, right? We're using the component form of vector subtraction, is this. And so what does magnitude of u minus v look like? Squared. So this is going to be what? u1 minus v1 squared plus u2 minus v2 squared plus u3 minus v3 squared. Let's expand that out because I'm taking these two and adding them together and then subtracting magnitude u minus v squared. So I'm going to expand this out. This is u1 squared minus 2 u1 v1 plus v1 squared plus u2 squared minus 2 u2 v2 plus v2 squared. Next one is plus u3 squared minus 2 u3 v3 plus v3 squared. So then, when let's see, well, let's just compute it all down here. So u dot v, we've already determined that it's 1/2 of magnitude u squared plus magnitude v squared minus magnitude u minus v squared. We now have expressions for all of those. It's 1/2 of. So writing this all together, so I'm going to take the sum of these two and subtract this term, this big thing I have here. Notice there's going to be some cancellation. So u1 squared is going to cancel out with u1 squared because I'm subtracting. Same with u2 squared, I can find a u2 squared there, and u3 squared, I can find it there. So all of that, magnitude of u squared cancels out with stuff that's in here. And really cool, same with magnitude v squared, right? I have a v1 squared here, get rid of that. A v2 squared here, positive, and this will be a negative. v3 squared, get rid of that, get rid of that. And I've totally canceled out magnitude u squared, magnitude v squared. What's left is minus 2 u1 v1. Oh, my signs are messed up. I'm going to have to figure out what's going on there. Minus u2 v2 minus 2 u3 v3. All right, so I typically don't want to restart making a video like this when I've made some sort of mistake. So something went wrong here. Why are these ending up as negatives here? Can you identify it? One of the reasons why I don't go back and just remake the video when I make a mistake like this is I want you, the viewer, to think about it for a second. What did I do wrong? Maybe you already found it. Maybe you're already saying, hey, Professor O, it's, you know, you made a mistake way back here. You should have fixed this. That's great if you already found it. If not, take a second, pause the video, and see if you can understand where I made a mistake, why these are coming out negative when I really should have a positive here, because we already know what we want it to be. Anyone find it? Well, I was subtracting u minus v squared. So I'm subtracting this whole quantity from these guys, which means I'm subtracting negatives. So that should be a positive 2u1 v1 plus 2u2 v2 plus 2u3 v3, right? I'm subtracting all of these quantities. That's why these canceled out, and these will turn positive. And so what do we have now? Bring this 1/2 through. We end up with u1 v1 plus u2 v2 plus u3 v3. And that's u dot v. So it's pretty awesome that we have this super nice form for the dot product. And remember, at the same time, the dot product is magnitude u times magnitude v times cosine of theta. So we have a way that involves not caring about what the angle is between the two vectors, not having to think about all that geometry. We have a purely algebraic or arithmetic way to come up with the dot product. It's pretty sweet. We're actually going to be able to do some cool stuff with this because now I have an expression. If I know my two vectors, I know their components, but I don't know the angle between them because, like I said, it's hard to find that in, say, 3 dimensions. We'll be able to recover what cosine of theta is and therefore what theta is by computing a dot product. All right, we'll see that in the next video. I'll see you there.